Hello students, in the GATE computer science series we were discussing the concept of layering in computer networks. Actually we have released two videos earlier. In the first part we discussed about what is a computer network, then the types of network, etc. And in the second part we discussed about MANET and the type of network topologies. Now in this part of the video we will be covering the concepts of digital to digital conversion. Actually data can be of two types, which the first one is analog data and another one is digital data. So what is the difference between these two? Analog is mostly concerned with the real world data actually. So if now I am speaking, right, my voice will be transmitted through air in the form of signals, like which is analog waves. So in real world everything happens in an analog fashion, like you may have an analog weight machine, everything analog. Usually real world items are analog, but digital in the sense interpreting data in a form that only a computer can understand. So in digital the data will be encoded in the form of binary bits, which is 0 and 1 usually. So why do we need a conversion actually from the analog to digital part? Let's assume that I just want to send a voice message through WhatsApp to my friend's mobile. So if I am communicating, if I am recording the message, my voice will be transmitted through analog waves to the mobile phone actually, since in the air, like in the radio frequency, through air only analog waves can pass. Digital waves cannot be passed through the air or through the radio frequency medium, etc. Hence, so my analog sound waves are recorded and it will be converted to digital waves so that my mobile can understand the message actually. So then again it will be converted to analog and it will be transferred through air or any channel, like the transmission channel. It will be passing as an analog wave. After reaching the friend's destination, it will be again transmitted to digital device so that the device can understand, and again when the friend is listening it will be broadcasted as an analog wave actually. So we need conversion from analog to digital, then digital to analog. There are mainly four types of conversions, which is analog to digital, digital to analog, analog to analog, and digital to digital. So in this video we will be discussing about the digital to digital conversion, and there are three types in digital to digital conversion, which are scrambling, line coding, and block coding. Digital to digital conversion is just basically like converting a digital data to digital signal. So in this what data actually means, the smallest unit of information, which is usually represented by bits. Like this is one data bit, and each individual digit is one data bit, we can say. Like a signal is a collection of data, like collection of bits actually, it encoded as a single signal. So when a sender wants to transmit the data, actually the data will be in computer understandable format. Data will be in the form of like digital bits actually, like a series of bits which will be encoded, then it will be transferred as a digital signal. So digital signal, it contains a waveform. So for 1 the data may be having high voltage, and for 0 it will be having a low voltage. So this digital data will be converted to a digital signal, and it will reach the receiver side, and then this digital signal will be decoded back to digital data, and only then the receiver can understand the data. So the digital data, like there are two more concepts, like the data rate, and one more is signal rate. Data rate is like the amount of data that gets transferred in 1 second. For 1 second, how many bits of data got transmitted, that is called the data rate. It is usually measured in bits per second, like per second how many bits got transferred. And then signal rate is actually the amount of the number of signal waves that got transmitted per second. It is actually measured as baud rate or signal rate. This is the unit of signal rate actually. Then let's now watch the difference between a signal element and data element. So consider this example. Here each bit is a data element actually. So while encoding, for each bit they have generated a waveform for each signal waveform for each particular bit. For each data element, one signal element is recorded. So So one data element for one signal element. The second category is for one data element, two signal elements are generated. See, for the bit 0, actually two waveforms, two signal elements are got generated here. And in the third example, for each signal element, it encompasses two data elements, actually four. So in this single signal element, it actually carries two bits like 0 and 1. And in the fourth example, actually we can see that four data elements got encompassed inside three signal elements. So what can be an effective conversion, like whether the data element should be higher or the signal element should be higher? So for efficient transmission, we just need to increase the data rate and decrease the signal rate. Increasing the data rates in the sense increasing the number of bits that gets transmitted per second, increasing the bits per second, and decreasing the signal rate in the sense decreasing the number of signals that get transmitted per second. So for effective communication, like we need to increase the number of bits that gets encompassed inside a single signal unit. So within one signal unit, we need to encompass so many bits as possible in order to avoid interference issues and all. The next main common thing is the synchronization issue. Actually, consider if two devices like A and B, the sender and receiver, they want to communicate data between them. Both the devices should have the same clock rate. Actually, you know about clock rate, right? Each device has its own clock. It should be synchronized with a global clock. Actually, for example, if you are accessing your internet through Google Chrome or any Google server, and consider your local device time is like very old, it is showing a very outdated time. It's showing January 1, 2000, like, or January 1, 2002. It may be showing a very old time interval. In that case, the Google server, what will it will notify you means it shows a clock error. It will say you need to update your clock with the internet server. Only then you can view the website Google. We can view the Google search result. It will say, it means the clock should be synchronized at both the sender side and the receiver side. Only then effective communication can take place. If the clock is not synchronized between two devices, what happens in the sense, the receiver can misinterpret the data and decode wrong signals. Actually, here consider the data that got transmitted is 101110001 actually, but due to clock error, a different data got transmitted, like the receiver has decoded a very wrong signal. This error happened mainly due to lack of synchronization between the two clocks. The first category in digital to digital conversion is scrambling. So just I told you, right, there are three main techniques actually: line coding, then block coding and scrambling. The line coding is mandatory for every data transmission. We just need to do the line coding, but the block coding and scrambling are optional. Like if you want it, you can encode it as well, or else you can just skip it. Scrambling is just like hiding the sensitive data so that normal people can't view it. For example, if you are filling a form, like when you are filling your name will be visible on the screen, but when you are typing a password, it won't be visible. It will be showing like star. It is just like hiding the sensitive data so that common people, they can't see. For example, if you have watched any news channel, they might have blurred the face of the victim so that the privacy of the victim won't get tampered. So scrambling is such a thing only. So while encoding, you can just scramble the sensitive data and send it to the receiver. So in order for a receiver to view the data, actually the receiver should have a descrambling unit at his side. Only then he can access the data, access the sensitive data. So there are two types in scrambling, which is B8ZS and HTB3. Let's see about them. B8ZS is bipolar with 8-0 substitution. See, consider the sender has transmitted a digital data which is 1 followed by 8 zeros actually. The problem here is that like when this digital data gets converted to signal, maybe it will be like for 1 it will be showing a high voltage, for 0 it will be showing a 0 voltage, right? So the signal waveform will be remain the same for all the 8 bits. The main issue will be like while decoding, the receiver can't understand like what is the interval between two frames. They can't distinguish between two consecutive zeros, and they may decode it to a wrong signal actually. This is called the baseline monitoring. We should try to avoid the baseline monitoring. So in order to achieve that, in this B8ZS technique, what they do is, if they encounter any 8 consecutive zeros, they will replace it with a different bit like 000 VB0 VB. So here the one, since it is bipolar, yeah, we'll discuss about the bipolar concept later. Just now, as of now, you just try to understand how the 8 zeros get substituted with 000 VB0 VB. So for the one, high voltage is high voltage signal is generated, and for the 8 consecutive zeros, initially 3 zeros they have substituted, then is B. And the V bit, what will be the value of the V bit is that it will be same as the previous non-zero pulse rate. Here the non-zero pulse rate is showing a high voltage level, like positive voltage, but in the positive pole. So the V will also be having the same value like the positive pole. And next it is a B. The B will be opposite of the previous, like opposite of the previous signal. So V is showing a positive polarity, so B will be carrying a negative polarity actually. Then next is 0 bit. So 0 bit will be in the 0 level, and V bit will just copy the value of the previous not zero pulse rate, which is negative voltage. So V will also be the negative voltage, and then B. So just now we saw, right, B will be the opposite of the previous non-zero pulse rate. So here it is a negative pulse rate, so B will be a positive pulse rate. Consider one more example here. In this example also, 1 is followed by 8 zeros actually, but the 1 here is encoded as a negative voltage level. So during substitution, the 8 zeros get substituted by 000 VB0 VB. So the initial 3 zeros it gets replaced, it will be the same. And for the V bit, what will be the value of the V bit? It will just look at the value of the previous non-zero pulse rate. So here it is negative voltage, so this pulse will also be negative, and then B value will be just be the opposite of the previous non-zero pulse rate, so it is shows positive. Then 0 will be in the 0 level, and then B will take the value of the previous non-zero pulse rate, so it is again positive, and B will be the opposite of the previous non-zero pulse rate, so B is negative pulse. So this is B8ZS encoding. When you see 8 consecutive zeros, it will be replaced by 000 VB0 VB. The second type is HDB3, which is high density bipolar 330. Here what they do is, if they encounter 4 consecutive zeros, the 4 consecutive zeros will be replaced by either B00V or 000V. So if while decoding, the node will check whether the number of zeros, like it has nearly 4 consecutive zeros, right? So the node will count the number of non-zero pulse rates actually. Here we don't have any non-zero pulse, everything is 0. So it will take it as a even number of non-zero pulses. So in that case, in even situation, the 4 zeros will be replaced by B00V. If the number of non-zero pulse rate is the 1 or like odd, it will be replaced by 000V. For example, if the signal is 11, then 4 consecutive zeros means this 11 will be encoded as it is, and for the 4 consecutive zeros, since the number of non-zero pulse rates is 2 here, which is even, these 4 zeros get replaced by B00V. For example, if there are 3 consecutive ones followed by 4 consecutive zeros, so the number of non-zero pulse rate is 3 actually, which is odd. So these 4 zeros gets replaced by 000V while encoding. So consider this example. Here we have 11, 4 consecutive zeros, then 1, and then 8 consecutive zeros. So these 1 For the first one we have a high voltage level, and for this next one we have a low voltage level. This is bipolar. This is concerned with bipolar actually. We'll discuss in detail about when discussing the bipolar concept. Just now ignore it. So we have 4 consecutive zeros. Since we have 4 consecutive zeros, we need to count the number of non-zero pulses, which is 1 plus 1. So we have two non-zero pulses here, which is even number. So these four consecutive zeros gets replaced by B00V. So what will be the value of B? We just now saw, right? B will be the value of it will be the inverse of the previous non-zero pulse rate. So here it is a negative voltage, so this B will have a positive voltage level. So then B00V, right? So these double zeros will be in the zero level, and the V will have the value same as the previous non-zero pulse rate. So this is having a positive pulse, so this will also have a positive pulse. Next is 1. So this is inverse actually. We'll deal about it while discussing the bipolar concept. Then after that we have 8 consecutive zeros. First just look at the first 4 consecutive zeros. For these consecutive zeros we just need to count the number of non-zero pulses. So while counting we have to ignore, like here we have substituted, right? This part we just have to ignore. After substituting only we have to count the number of non-zero pulses after substitution. So here this one only must be counted. These 2 ones should be ignored because we have done the substitution. Now this part is different now. So in here we have only 1 non-zero pulse, so which is odd, right? So these 4 consecutive zeros will be replaced by 000V. So 000 and V. The V will take the same as the value of the previous non-zero pulse, which is the negative voltage, negative pulse. And then we have substituted here. So this part it is over. Now again we have 4 consecutive zeros. So while checking for the number of non-zero pulses, we have after substitution we have 0 non-zero pulses, like everything is 0. We don't have any 1. So 0 number of ones. 0 is even, no. So we just have to replace this 4 consecutive zeros by B00V. So B00V. So B value will be the opposite of the previous non-zero pulse. So this is negative. So B value will be positive. Then 2 consecutive zeros and then V. The V value will be same as the value of the previous non-zero pulse. So it's a positive pulse. So this is HDP3. Next we can see about the line coding schemes. There are a few types in line coding actually: unipolar, polar, bipolar, multi-level and multi-transition. Before discussing about the line coding schemes, we just have to know the characteristics of the nodes that are taking part in this line coding. So the sender and receiver node, right, they should be synchronized. Their clocks should be synchronized in order to avoid the errors and the interference issues and all. Then the network should be less complex and baseline monitoring should be very less. Baseline monitoring, just now we saw it, right? If you are sending immediate consecutive zeros, too many consecutive zeros from the sender to the receiver finds it difficult to decode it. Since there are consecutive zeros, they can't know the difference in signal between these consecutive zeros, so they may decode it to a wrong signal. So in order to avoid that, this decoding to a wrong signal, it is called as baseline monitoring. So this drift should be avoided. The first part is non-return to zero. NR reset is non-return to zero. Here two categories are here: NR reset level and NR reset inverted. So in NR reset level, here the bit 1 will be represented as a high voltage. So 1 may be having a voltage level like 10 volt or 5 volt, it depends on our network specification, and 0 bit may be represented as 1 voltage or 0 voltage, any low voltage level. So here non-return to zero, this return to zero, this concept may be, you may feel it is a new concept or why is it included here, but you may get an idea once we discuss about return to zero actually. So in non-return to zero, the bit 1 will be converted as the same, like high voltage. For the 0, it will be showing a low voltage, the signal will have a low voltage level. Again for 1, a high voltage pulse. For 0, it's a low voltage pulse. So again 0, the same low voltage pulse, again 0, the same low voltage pulse remains. Then again 1, when we encounter a 1, it will be transmitted to a high voltage pulse, again the same 1, so the same high voltage level remains. Then for 0, it shifts from high voltage to low voltage. Then in non-return to 0 inverted encoding, what we do is, for 1 there will be a transition. For whenever we see a bit 1, inversion occurs. Like if there is a high voltage, it will be converted to low. If there is a low voltage, it will be converted to high. And whenever we see a 0 bit, it will copy the previous bit's value, actually the same, no change occurs. So here 1, when we encounter a 1, it just shifts from high voltage to low voltage, and when we encounter a 0, 0 means no change. So the same thing gets repeated here. Again we see a 1. Now we have to, inversion happens, right? So low to high, so low should be converted to high. Then we have 3 consecutive zeros. For zeros means no change, right? So this high voltage pulse remains. Then after seeing a 1, we do an inversion, which is converting from high voltage to low voltage. Again we encounter a 1, again conversion from low voltage to high voltage. Then we have a 0, so no change, the same high voltage. This is NRZ level and NRZ inverted encoding schemes. Then we have unipolar non-return to 0. Unipolar in the sense we only have one pole, actually, like positive alone. So the value of the signal will be ranging between 0 to any predefined voltage, so only the positive range. So if we encounter a 1 bit here, it will show a high voltage level. For 0 bit, 0, the value 0 remains. So only there are 2 values. For bit 1, high voltage signal will be generated. For bit 0, 0 voltage. Again for bit 1, high voltage. This voltage value may be 5 volt or 10 volt, it depends on your network requirements. Then for the bit 0, the same voltage 0. Then for the bits 1, again high voltage. For bit 0, again 0. It is very easy, like a simple one. Next comes the polar non-return to 0. Polar in the sense, 1 bit will be, if 1 bit has a positive voltage, the bit 0 will have a negative voltage. So that's the thing, the swapping between the positive and negative. So value will be like plus 5 volt or 10 volt, then the 0, then negative voltage. So whenever we encounter a 1, the value will be the plus 10. Like if it is a 10 volt, it will be 10 volt. For 0, it will be minus 10 volt, minus value. Again for 1, it is plus 10 volt. Again for 0, it is minus 10 volt. The same. Swapping between the positive and negative values while encountering a 1 and 0, it's called the polar non-return to 0. Then bipolar. In bipolar, what happens is that whenever we encounter a 1, it will be either positive or negative. The first one we see may be having a positive voltage, but the next one we see it should have a negative voltage. But for the bit value 0, the same value remains, like no change. It will be 0. So for 1, now we have applied a positive voltage. So for 0 bit, the 0 level remains 0. So whenever we encounter a next 1 bit, it will be the opposite. So here we had a positive voltage, like positive pulse. So the next one will have a negative pulse. For the next one, positive, negative, positive. So this is what happens. So for the first one, we had positive, then for 0 voltage pulse, and then for the next one, negative voltage. For 0, it is the same 0. For the next one, it is positive, so high voltage. Then for the low voltage, for the next one, again high voltage. Then for 0, it is 0. Like swapping between positive and negative for the alternative ones. It is called bipolar non-return to 0. And then we can see about return to 0. What do you mean by return to 0? Return to 0 is like when transmitting a signal from data from a bit to a signal. If it is a 1, like it will be transferring. 1 will be showing a high voltage level, like right. So after passing the signal, after half of the midway, once the signal is traveling, in the midway actually it will return back to 0. That is what return to 0. For example, now let's see here, right, it is unipolar, right, so it will be having only between 0 to like 5 or 10, only positive range, no negative here, only one pole is only present here, unipolar. So for 1, usually in non-return to 0 unipolar we had the same range, like the complete 1 was here 1 completely high, but in return to 0 what we should do is the 1 voltage, the value for 1 it will show him a high voltage rate, but after traveling midway it will just return to 0. But for zeros it will be the same 0, completely 0. Then again for the next 1 bit the voltage will increase, then after traveling midway it will again return back to 0. Then next is 0, the same 0, again 0. Then for the next one the voltage level will increase, but after traveling midway it will just return back to 0. Then again 1, so voltage increases, after traveling midway it returns to 0. Again voltage increases, after traveling midway it returns back to 0. Then again 0. This is the main concept of return to 0. The next one is polar return to 0. Just like in non-return to 0, in polar for 1 may be having a positive voltage level and 0 will be having a negative voltage level. So for 1 it will be like a positive voltage, then after traveling midway return to 0. Likewise for 0 it is not like 0, since it is polar, 0 will be having a negative value. So for 0 the voltage goes to negative range, and then after traveling midway it returns to 0. Then again for 1 positive voltage, after traveling midway returns to 0. Then for 0 negative voltage, after traveling midway returns back to 0. Again 0, so negative voltage after traveling midway returns to 0. Then 1 positive voltage, after traveling midway returns back to 0. Again 1, so positive voltage after traveling midway return back to 0. Again 1 positive voltage after traveling midway returns back to 0. Again for 0 it is like a negative voltage, after traveling midway returns back to 0. This is polar return to 0. The next one is bipolar return to 0. Bipolar return to 0 in the sense, in bipolar we have, for first one we may have a positive voltage, but for the next one we will have a negative voltage. For 0 this a 0 level remains. So after for this first one, if it is a positive voltage, the next one will have a negative, next one will have a positive, negative, positive, like alternate ones may have a positive value, the remaining may have a negative value. So for the first one voltage increases and then returns back to 0. This for the 0 it will be the 0, same. For the next one it is negative, so negative voltage after traveling midway returns back to 0. Then it will hold the value 0 for the 2 0 bits, and then encounters a positive 1, so high voltage, then return back to 0. Then for the next one it's like negative voltage, then return back to 0 after traveling midway. Then for the next one it's like positive voltage, after traveling midway return back to 0. Then for the 0 it is completely 0. This is bipolar return to 0. Then we have biphase Manchester and differential Manchester. This is same as the previous one actually, some more or less same, but here in Manchester what happens is like for 0 the value will be shifting from high to low. For 1 bit it will be like low to high. For example, on seeing input data bit 0, the voltage drops from high voltage to low voltage. So here again 0, so drops from high voltage to low voltage. After encountering a 1 means low to high, so low voltage to high voltage. Then again 1 low to high. For 0 high to low. For 1 low to high. For 1 again low to high. Then for the next 0 high to low. This is Manchester encoding. Differential Manchester encoding is the same actually, but the roles gets inversed actually. After the consecutive 1 bits, they may have follow an inversion actually. So here in differential Manchester, 0 will be following a high to low actually, but for 1 it will be either low to high or high to low. For example, if the first one here follows low to high, the next one we see in the the data, it follows high to low, and the next one will follow low to high, like inversion in an alternate manner. So here for 0 it's high to low, right? High to low, again 0, high to low. For the first one we have so low to high, low to high. For the next one we encounter here, it will just do the inverse of the previous one. So this did low to right, so this will do high to low. The next 0, for 0 it's like high to low. Again for 1, the 1 will do the opposite of the previous one. So this one did high to low, so this will do low to high. And then the next one will do the inverse of the previous one. So this did low to high conversion. So this bit will, for this bit the corresponding signal will be high to low. Since this is low to high, it will be high to low. And for 0 it's as usual high to low. Next we can see about bipolar AMI and pseudo ternary. AMI means alternate mark index. In bipolar AMI, you might have known already, since it's bipolar, the consecutive 1 bits will show an inversion property. Like if the first 1 bit had a positive value, voltage pulse rate, the next 1 bit will have a negative pulse rate. So for this positive, negative, positive, negative, positive. So for the 0 bits it will be the 0. For the first one positive. For 0 it is again 0. For negative, for the next one it is negative, so low voltage. Then again it's high voltage, 0 voltage for the consecutive zeros. Then since it's negative, so negative voltage. Then again it's positive, inversion, opposite. This happens in bipolar AMI. But pseudo ternary is just the opposite of bipolar AMI. In here the 1 bit will have the same value, like the same range. For the consecutive zeros it will be having a positive and negative value in an alternate fashion. For example, the first 0 may have a positive value, the next 0 will have negative. So based on 0 inversion happens. It's positive, here it's negative, here it's positive, negative. For 1 it will be the same level, 1 for 1. So for the first 0 it is positive, for 1 it is the same midway, for the next 0 it is negative, then the next 0, for the next 0 it's positive voltage level, then for the next 1 it remains the same, right, midway, next consecutive 2 ones, then for the next 0 it is negative, for the next 0 it is positive, then for the next 0 it's negative voltage level, and for the next 2 consecutive ones the same voltage level remains the midway. So this is about bipolar AMI and pseudo ternary. Next we can discuss about block encoding, which is the third category in digital to digital conversion. In block coding what happens is, like, it is mainly used for error correction. Here the main aim is just like adding redundancy bits. For example, if there are 4 bits in a data, it will be transferred to 5 bits, like extra 1 bit is added to ensure error correction and proper delivery without error. So here the encoding, how it happens in the sense, the digital data, it will be split into different, like, since here this is the input part actually and this is output, like, so it will be split into 4 bits actually, the entire input data, digital data. Then each 4 bits will be encoded to 5 bits. So separate 5 bits will be generated, and after that they will be merged together as a single digital data, and it will be sent to the receiver, and the receiver will decode it and then get back the original signal. So for the each sequence, this will be the resultant. Like, I have demonstrated a few examples, like how the 4-bit sequence gets converted to a 5-bit sequence. The second category is 8-bit bar 10-bit. So with the 8-bit input, it will be converted to 10-bit input. It is actually a combination of 5-bit 6-bit encoding and 3-bit 4-bit encoding. This is efficient than the previous one. So in this video we saw about the digital to digital conversion, which is scrambling, line coding and block coding. In next video we will be watching about analog to analog conversion, analog to digital conversion and digital to analog conversion. That's all for today. Thank you.